Greetings to everyone and welcome to Acadex Higher Engineering Academy, building your engineering career. Today in this video, we are going to be looking at the complete accurate solution to Nahpi 2020 Physics Paper 2, the National Higher Polytechnic Institute of Bamenda, and the concepts are going to be well explained in this video. For the sake of self-presentation, I am Godwill Yakum. So the paper is supposed to be written for 1.5 hours duration, and we have some constants that are useful in the exam that we're going to be using as we're going to be solving the 30 questions in this video. So we have a complete session of a complete all-in-one video. So get ready with your pen and your notebook and solve along with me. Let's get started with question number 1. Question 1 reads: a bucket is swung in a circular path with an angular acceleration of 20 rats per second at a radius of 1.250 centimeters. What is the linear velocity and acceleration when the bucket reaches an angular velocity of 25.0 rats per second? Alright, so what's the question asking us to do? What is the linear velocity and acceleration? So that's what we're looking for. We're looking for the linear velocity and acceleration. Now, we have to start by collecting the data that has been given to us. We have been given the initial angular velocity of 20.0 rad per second. We've also been given the final angular velocity and what? The radius of circular path, which it's important we start by converting it already to meters, because it's going to be important. That's what we're going to be using. Alright, now calculating the linear velocity. First, we know that v, the linear velocity, is equal to r, the radius of the circular path, times omega, and omega is the angular velocity. Now, angular is the angular velocity, and v would therefore be equal to what? 25 times 1.25 times 10 to the negative 2 meters, which is what? The radius of our circular path, times omega, which is the 25 rats per second, because the bucket was swung in a circular path with an angular velocity of 20 at a radius of 1.250 centimeters. Now we are calculating the linear velocity and acceleration when the bucket reaches an angular velocity of 25.0 rats per second. That's why this is the velocity that we are using. This is the initial velocity, and at the point that we are calculating the linear velocity, we are at this velocity of this angular velocity of 25.0 rats per second. So that gives us a linear velocity of this. Now, calculating the linear acceleration, we are going to use the Fresnel reference. In the Fresnel reference, the acceleration of the center of gravity of an object is always equal to two components. We have the tangential component of that acceleration and the normal component. So let me illustrate what the Fresnel reference is all about. Alright, so we have a circular path like this, and the acceleration along this circular path is equal to, at any point, is equal to the sum of these two components, the tangential component and the normal components of the acceleration. Now, the tangential component of the acceleration is always given by dv dt, this one. Meanwhile, the normal component of the acceleration, which is directed toward the center of the circular path, is always equal to v squared over r. Now, it means that the acceleration of the center of gravity of that object is ag, which is equal to a tangential plus a normal. And we have that, substituting, we have that is equal to dv dt plus v squared on r. And then now dv dt is actually equal to 0. Why is it equal to 0? Why is dv dt equal to 0? Because the acceleration is there's no acceleration in this, along the tangential component of the acceleration is 0, because there's no acceleration along this path. Therefore, we have that at is equal to 0. So all the acceleration that we have is v squared on r, which is along the normal component of the acceleration. So that's why now dv dt becomes 0, and then equal to 0 plus v squared on r. Therefore, the acceleration of the center of gravity is given simply by the normal component of the acceleration. Alright, so we'll do the numerical application, and we have that the acceleration, the linear acceleration is 781.25 times 10 to the negative 2, and therefore we can now conclude that the option that has the correct answer is A. Question 2. This is what we have for question 2. It reads, the diagram in figure 1 shows the graph of the displacement s against time t for an object moving in a straight line. Which of the following graph of velocity against the time represent the motion of the body over this period? Alright, so this is the displacement time graph that has been given to us, and we have option from A to D. We have A, B, C, and D, and we have to verify which one of them is the correct velocity time graph for the motion of that body in this period. Okay, now I'm going to draw a diagram to explain how the velocity actually varies with time. So I'll start with my axis, the y-axis, and the x-axis. Okay, velocity time graph. So we have the velocity v and time t measured in second. All right, now we have the origin O, and when the velocity time graph is represented as such, we have a constant acceleration. So meanwhile, this represents a constant deceleration, or a negative acceleration, a negative constant acceleration, which is deceleration. And this is what? A constant velocity. A constant velocity, meaning that the motion the motion of the body is constant. It's not accelerating. Here it is accelerating constantly, uniformly, sorry, and then here it is decelerating uniformly. Now let's examine in the case of this. it is covering a certain distance in a certain time interval, and then it starts from the origin and accelerates, and then it goes back to the displacement of 0. So this is what we have. Alright, we're going to have this. The body starts by this is the velocity time graph. It starts, we have a uniform acceleration like this, and then after that we also have a uniform deceleration, and then the only graph that corresponds to this is A. So we'll choose A as our correct answer. Alright, let's just proceed to question 3 first. A light incident on a 0.15 millimeter wide slit forms a diffraction pattern on a screen 6 meters away. If the first minimum of the diffraction pattern is 2 centimeters from the central peak, what is the wavelength of the incident light? The wavelength of the incident light, that's what we're looking for. Wavelength of the incident light. Now, to determine the wavelength of the incident light, we will use the single slit diffraction formula, which is given by what? Given as sine theta equal to m lambda over a. Now, where theta is what? Theta is the angle of theta is the angle of the minimum, and lambda is the wavelength. M is the order of the minimum, and then A is the width of the slit. First, we need to find theta, and since the screen is 6 meters away from the minimum, is 6 meters away. The screen is 6 meters away from the slit. Sorry. Since the screen is 6 meters away from the screen, and the first minimum is 2 centimeters, which is the same as 0.02 meters from the central peak, we can use the tangent function, tan theta, and tan theta is given by what? Opposite over adjacent. So we're going to have theta to be what? The tan inverse, or the arctan of 0.02 over 6. Now, let's plug in the values we have in the single slit diffraction formula sin theta equal to m lambda over a, and then we're going to determine the value of lambda, which is our wavelength. So we're going to have that lambda for the first minimum, since we already said that m is the order of the minimum. So for the first minimum, m is equal to 1. So we'll simply have sin theta equal to lambda over a, and then lambda will be what? Equal to a sin theta. Now we need to convert the slit width to meters, because it was given to us in millimeters, 0.15 millimeters. And then converting from millimeters to meters, we'll divide by 1000, and then we're going to have this. So we're left to solve and find out that lambda gives us 420 times 10 to the negative 9 meters, which is the same as 420 nanometers, giving us the option B as our correct answer. Proceed to the next question. Light has frequency of this. How many wavelengths of this light are there in a 1 millimeter thick piece of glass with an index of 1.5? Solution. a light has frequency of this, the frequency of that light has how many wavelength of this light are there in a 1 millimeter thick piece of glass. So let's consider this to be our piece of glass here. And we are told that this piece of glass is 1 millimeter thick. So alright, now we are told that the thickness of our glass is 1 millimeter, and the 1 millimeter is the same as 1 times 10 to the negative 3 meters. The frequency was already given to us, and then the refractive index was also given, and we're going to use c, which is the speed of light, which was given to us as a constant already. And then from our diagram here illustrating the piece of glass, if this represent the n waves that the light forms in the glass, then we are going to have that T, which is the width, the thickness of the glass is equal to n lambda, and n will therefore be equal to the number of wavelengths. Alright, so that's the idea that we're going to use to solve this question. From t equal to n lambda, n will be equal to t over lambda, and we also know that lambda is equal to v over f. This means that substituting, we're going to have that n is equal to tf times the refractive index divided by c, where c is the speed of light in a vacuum. Okay, let's do our numerical application. I'm going to have that n is equal to 2.37 times 10 to the 3. So we have option B as our correct answer. The volume of an object as a function of time is calculated by this, where t is time measured in seconds and v is in cubic meters. The SI unit of the constants a and b are. This question has to do with homogeneity. So I'm going to start by making some basic recall. What is a homogeneous equation? A homogeneous equation that we all know is an equation in which the base unit of the additive terms of the physical quantities on the left hand side of the equation equals the base unit of the additive physical quantities on the right hand side of the equation. Then we call the equation a homogeneous equation. Now the equation that has been given to us is v equal to 80 cubed plus b over t, and we're being told that v is the volume. Now it means if v is volume, then the unit of volume, the base unit of volume is meters cubed, and t is time, meaning that the unit of t is what? Seconds. Okay, now the base unit on the left hand side of our equation, on the left hand side we have just the volume, and the base unit on the left hand side will just be meters cubed. So now let's proceed to the right hand side. On the right hand side we have the unit of a times the unit of t cubed, and the unit of t is seconds, so we simply have the unit of a times second to the power of 3 plus the unit of b times second to the power of negative 1. Now let's equate the base unit on the left hand side and the right hand side, and then we're going to have this we're going to have this, and then we can conclude that the base unit of A is going to be meters cube per second cube, while the base unit of B is going to be meters cube second. Therefore, we have option A as our correct answer. An electron moving along the x-axis has a position given by x equal to this meters, where t is in seconds. How far is the electron from the origin when it momentarily stops? Okay, that's the question. Now we're being told that our electron is moving along the x-axis. So this is our x-axis here. Then this is the equation that gives us the position of the electron at any time t. Now let's evaluate the position of this electron at time t equal to 0. When t is equal to 0, we have x also equal to 0. This means that the electron start moving from here, from this origin, because at time equal to 0 initially, the electron is here. Now, at any time t, the position of the electron is given by the equation x equal to 16t e to the negative t. Now, we know that the velocity is given by the derivative of displacement with respect to time. Therefore, v is equal to what? Dx dt. And for us to have the velocity, we shall have to differentiate the equation that gives us the position of this electron, and then differentiating this function, we have 16 times 1 minus t, or that times e raised to the power of t. Now, why are we differentiating? We know that when the electron momentarily stops, it means that the velocity of that electron becomes 0. So we need to find the time when it stops. And when it stops, v is 0, meaning that we equate this velocity that we have to 0. When the electron momentarily stops, v is equal to 0, meaning that the equation of v, 16 into 1 minus t times e raised to the power of t, is equal to 0. And we have that t is equal to 1. To have the position of the electron at this time, we have to substitute t equal to 1 in the original equation that gives us the position of the electron at the time t equal to 1. And then we now have x to give us 5.89 meters. Option A has the correct answer. Each diagram below shows 3 Newton meters in a two-dimensional arrangement joined to demonstrate a system. 3 forces acting at a point. The reading represents the magnitude of the forces. Which system of forces could be in equilibrium? Alright, so here we are to determine which of these 4 systems could be in equilibrium. Voila. So let's get started. We have to make a little recall that will enable us to solve this problem accurately. Now, for a system of forces to be at equilibrium, the fundamental relation of dynamics for a body in equilibrium must be verified. And we know that from TCI, we know that the sum of the total external forces on a body in equilibrium is equal to 0. In equilibrium, we simply mean at the time when all the forces acting on that body at that point sum up to 0. So from the TCI, theory of the center of inertia, the sum of all these forces should give us 0 for a particular system, then the system is in equilibrium. We shall start by annulling option B already, because we look at the direction of motion of the direction of the forces of the component forces. Here we have the 3 Newton force this way, 4 and 3, and the resultant of these forces will be an upward force. So we don't need any magician to come and tell us that option B is already wrong. We can start by eliminating it, and then we are left with 3 options. We shall also continue to eliminate option D. Why? Because looking at this system critically, the system will never be at equilibrium because of the magnitude of the forces that are acting in all these directions. The resultant force will not be 0 after resolving the forces. Now let's go to C. We are going to resolve this force and compare with this. But now, if you resolve this force of 3 Newton, this 3 Newton force and this 3 Newton force here, the resultant will fall here. And it's not going to be 6. It's not going to sum up. Therefore, it's not going to annul the effect of this. It means the resultant force will be moving this way. Therefore, C is also a wrong option. Now let's go to option A. We have these forces. The 3 Newton force acting upward vertically, and the 4 Newton force acting horizontally to the right. The resultant of these two forces will be here, and we are going to use Pythagoras theorem to find the total resultant force of these two forces, the 4 Newton and the 3 Newton forces. 3, 4. We now use the Pythagoras theorem to have that the resultant force here is 5 Newton, and the 5 Newton force is acting along this line. Now, what do we notice? Hence, the system now becomes, we originally have a 5 Newton force that was moving this way, and then now we also have another 5 Newton force that is opposing the motion. So we have a 5 Newton force moving down this way, and another 5 Newton force that is opposing the motion at an angle of 180 degrees. Therefore, system A is at equilibrium because the total force, sum of the forces acting at this point will give us 0. Therefore, the system A is in equilibrium. If D is the distance between the slits of the and the screen in a Young's double slit experiment, and the two slits are separated by a distance equal to twice that of the wavelength, then the fringe width will be okay. We have that the fringe width is given by this equation, beta equal to lambda d over d, where capital D is the distance between the screen and the slit, and small d is the distance between the slits, then lambda is the wavelength. Now, the two slits are separated by a distance equal to twice the wavelength. It means the slit separation is equal to 2 times the wavelength. It means the slit separation small d is equal to twice the wavelength. Please be careful. It was not said that it is twice the wavelength, but it is equal to twice the wavelength. It means that it is equal to 2 times lambda, which is the wavelength. So now, if we substitute back into this equation that d is equal to 2 lambda, we are simply going to have this, and the lambdas will cancel. So we just want to have that. We just want to have the expression for the width, for the fringe width. When the lambdas cancel, we are left with the fringe slit separation, which is capital D divided by 2. So we have option B as our correct answer. Option B is correct. Alright, number 9. A motorcycle's long rider moving horizontally takes off from a point 1.25 meters above the ground. He lands 10 meters away from the takeoff point as shown in figure 2. What was the speed at takeoff? This is the 1.25 meters above the ground, and then this is the takeoff point. So we're expected to find the speed at this point, and then so let's see what to do. Analyze the question and start solving. This question has to do with projectile motion. So now, what is a projectile? What's a projectile? Or what is projectile motion? Projectile motion is a type of motion that an item or a particle, and that particle is called a projectile, experiences when it is near the Earth's surface and moving along a curved route only due to gravity. So in a projectile motion, the only force that's acting on that on the body at that time is the acceleration due to gravity. Now, since the motorcycle takes off horizontally, its initial velocity is equal to 0 because it takes off, it starts like so. The initial velocity is equal to 0, and now the vertical distance moved was given to us as 1.25. So now we have that s is equal to 1.25 meters. Now let's use this equation of s equal to ut plus half at squared, and then we are going to have the time taken for it to arrive to have moved, the time taken for this particle to have moved this distance vertically, this vertical distance of 1.25. the time taken is 0.505 seconds. It means that it takes him 0.505 seconds to leave from here and drop down to this level. There is no acceleration in the horizontal direction, so the motorcycle moves with constant speed, and the speed is given by the distance traveled divided by time taken, and the distance is 10 meters in the horizontal, and the time taken, he also takes an equal time to travel horizontally, which is 0.505 seconds. And finally, therefore, we have the speed of 20 meters per second. Takeoff speed is 20 meters per second. Option Z is correct. Two identical 1.0 kilogram blocks of copper metal are initially at a temperature T1 0 degrees Celsius, and the other initially at temperature T2 100 degrees Celsius are enclosed in a perfectly insulating container. The two blocks are initially separated. When the block E are placed in contact they come to equilibrium at a final temperature Tf, T final. The amount of heat exchange between the blocks, the two blocks in this process is equal to which of the following? Now we are taking the specific heat capacity, the specific heat of copper metal, 0.1 calorie per kilogram. Okay, per kilogram Kelvin. Okay, now we know that when equilibrium is attained, the heat gained by the colder block must be equal to the heat lost by the hotter block, and then they will now reach an equilibrium when the two temperatures will be equal. So at equilibrium, theta 1 is equal to theta 2. So let's illustrate what we are having. Initially, this is what we had. We have the first block here. Let's say the colder block at T1, which is 0 degrees Celsius, and the hotter block at T2, which is 100 degrees Celsius. Now, this is what we have finally. When the two blocks are brought together, now we have T1 at this end. There's an intermediate temperature T that we are going to attain, which is now called the equilibrium temperature, and the T2, which is 100 degrees Celsius. And then at equilibrium, we are going to have these two temperatures to be the same, theta 1 and theta 2. Now, to solve this question, we must assume that there is no heat loss to the surrounding. Why are we free to assume that there is no heat lost? The question told me something very interesting. Are enclosed in a perfectly insulating container. So the blocks are enclosed in a perfectly insulating container, meaning that they are insulated against heat loss. Therefore, I am free to say that there is no heat lost to the surrounding, meaning that all the heat that has been lost by the hotter block is gained by the colder block, and nothing is radiated, nothing is no heat is lost to the surrounding. Now at equilibrium temperature, we are simply going to have the sum of the temperatures divided by 2, because there is no heat lost. And then if we go on calculating, since they are identical. What do we mean by two identical blocks? The blocks have the same properties. They have the same heat capacity, and now they have the same masses. So since they have the same properties, the properties will cancel out. So that is why we have just the sum of the temperatures and divide by 2. Hence, the amount of heat exchange between the two blocks is what? 50 kilocalories. 50 is there among the option? Option A is correct. Okay. Question. A rod of length 1.0 meter has a non-uniform composition, so that its center of gravity is not at the geometrical center of the rod, which would be halfway along its length. The rod is laid on support across two electronic balances, as shown in figure 3. The balances, which have been previously set to 0, give readings of 360 grams and 240 grams. Where is the center of gravity of the rod relative to its geometric center? Alright, so let's see the work that we have to do here. Let's evaluate the work the work we have to do, and then we start doing it. Let's analyze the question. This question, looking at the system, we already know that the only way that we can be safe is by using the principle of moment. We can only use the principle of moment to determine the position of the center of gravity, because now they are saying that the rod is non-uniform. It's not as it is drawn on the diagram. Since it is non-uniform, it means that one side of the rod is thicker than the other, either here or here. It means the rod is thick at one side and is thin at the other side. It does not have a uniform composition. Now the first thing I'm going to do is to convert the grams that were given to me to kilogram. Alright, that's it there. Then now I'll indicate the geometric center of the rod, which is halfway. And then since the length of the rod is 1 meter, it means that the center will be at the position of half meter. Then now I'll place my center of gravity, G. Why am I placing my G here? Because the rod is not uniform. Had it been the rod was uniform, then the center of gravity will be at the geometric center of the rod. But now, if the reading of these two measuring cylinders, these two balances, it's not measuring cylinder. This is an electronic balance, not measuring cylinder. These two electronic balances were set to 0 previously, and now this one gives a reading of 240 grams and here of 360 grams. This already tells us that this part of the rod is heavier than this one. Since it is not uniform, we now understand that this part of the rod is thicker than this one. Therefore, the center of gravity will be towards this one than the other one. So from the geometric center, it will be this way. That is why I place my G somewhere around here to be determined. Okay, that is my G, the center of gravity of my rod at a distance x from the center of gravity from the geometric center. Now, so after doing that, I start by cancelling option B to be wrong, because my center of gravity is already to the left. I've already seen that it's already to the left. So option D is also going to be wrong already. Alright, I'm now left with two things to choose from. Now I'm going to use the principle of moment. And then it's important to take moments about the center of gravity at equilibrium. Now I'm taking moment at equilibrium, meaning that I'm considering a situation where the clockwise moments are equal to the anti-clockwise moment. And now the only force that can cause the clockwise moments, that can cause the rod to rotate like this, is the weight. The force that is exerted, in fact, is the weight of the rod at this point. Meanwhile, the moment, the force, the only force that can cause the rod to rotate in the anti-clockwise direction is the weight of the rod at this point, and they are all given. So, taking moments about this at equilibrium, I'm going to just have my value of x. So I'll have this 2.4 times 10 to the negative 4. That's the mass, not just the mass. I need the weight, so I'll multiply by 9.8. Then now, times the distance. Remember, I'm taking moments. Now I'm taking the perpendicular distance from the pivot. My pivot, I'm taking moments about this position. So I'll have the distance of this force from this pivot is going to be 0.5 meter plus x. That's why I have 0.5 plus x. Meanwhile here the distance from the pivot will be 0.5 minus x, and then I'll have x to be equal to 6 times 10 to the negative 5 divided by 6 times 10 to the negative 4, and then 9.8. Okay, so I have x to be 1 over 10 or 0.1 meter. So option A. Now, note that the relativistic mass is the mass assigned to a body in motion. In classical physics, prior to special relativity, the momentum P and energy E assigned to a body of rest mass m0 and velocity v are given by the formulas. Now, this is the formula to have the momentum of a body that is moving at a speed at a high speed, in fact greater than or equal to the speed of light. And then this is the formula to find the relativistic energy. When the rest energy E0 is was undetermined. Now the relativistic mass is given by m0 equal to the gamma factor multiplied by m0, and then this is the formula to calculate the gamma factor, where c is the speed of light in a vacuum. So if we apply this, we are going to come out with our answer of 10 kilogram quietly, but with the explanation from here, our answer is 10. Our answer is 10 because when bodies move with a speed that is greater than or equal to the speed of light, their masses due to motion is always greater than their rest masses. So the sum of their masses due to motion must also be equal to the sum of their masses at their rest masses. Alright, so now for every rest mass m0, the energy associated to this rest mass is given by E0 equal to m0 c squared. It means that the relativistic energy is equal to the relativistic mass multiplied by c squared. But now we know that the relativistic mass, or the mass of that body due to the motion, is equal to the gamma factor multiplied by m0. It was stated in the formula on the other page. Therefore, the relativistic mass will simply be the gamma factor multiplied by m0 multiplied by c squared, and the gamma factor is given by this. Now, we are told that no energy is radiated away, and then from here it means that energy is conserved. Therefore, we are free to use the relativistic conservation equation. So I'm going to use the relativistic conservation energy equation. It means we are going to the equation is this: the relativistic energy of A plus the relativistic energy of B is equal to the relativistic energy of A and B. And then we're just going to equate because we already had them from up, which is going to give us this. This is the equation. Now in the question, we were also told that M A is equal to MB. So their rest masses were 4 kilogram, 4 kilogram. So they are the same. Their rest masses are the same, and they were moving at the same speed, except that A was moving in opposite direction of B, meaning that the magnitude of their speed was the same, which is 3 feet the speed of light. So we'll now just substitute it in the conservation energy equation, and then we're going to have that M is equal to 10 kilogram. So we'll now conclude with clear conscience that our answer is 10 kilogram. Therefore, option D has the correct answer. And now we move on to question number 5. How many revolutions will a person complete after initiating a spin at 5 revolutions per second and accelerating at the rate of 2 rads per second squared for 3 seconds? Now, for circular angular motion, the formula for angular displacement theta and angular acceleration alpha is given by this, where theta is the angular displacement and omega is the initial velocity, and we know that omega is the same as 2 pi f. So if we start equating from that equation above, let's call it equation 1, then we are going to have theta to be equal to this, and then now the number of revolution is equal to what? Theta over 2 pi because one revolution is equal to 2 pi. It means if we are calculating the number of revolution, we need to take the angular displacement and divide by 2 pi, and then from there we have number of oscillation equal to 16, number of revolution, we have 16 revolutions. Question: a deflated rubber balloon is placed on a digital balance and found to have a mass of 5.0 grams. It is inflated with air to a diameter of 30 centimeters and placed on the same balance, which now shows the reading of 5.7 grams. What is the magnitude of the buoyant force acting on this inflated balloon, inflated round balloon? Alright, so take note of this word. We are looking for the buoyant force, the magnitude of the buoyant force. I will also take note of the round balloon. It will help us. Now let's recall ourselves what the buoyant force is. Buoyant force, it is a force which comes into the picture when an object is placed in a fluid. It is mathematically equal to the weight of the fluid displaced by the immersed object, and then is given by rho v g, where rho is the density, v is the volume, and what g is acceleration due to gravity. Now, according to the question, these are the givens, the data that have been given to us. Let's start solving. Now, the volume of a sphere, that's why I said we need to take note of, we need to underline this, of the inflated round balloon. So what has been immersed in the liquid is what? Balloon. Is it just a liquid? It has been immersed in air. It's air, right? Balloon placed in digital balance and found to have a mass of this, inflated with air of diameter, voila. So where are we now? The balloon is a round object. It's a round object, so we're going to look for the volume because we need it. So I'm going to look for the volume. And the weight of the fluid that has been displaced will give us the buoyant force. Alright, so the volume of a sphere is given by pi radius squared on 3, pi radius square height. Yes, but now we are going to have the volume of this sphere whose diameter is 30 centimeters. So we are going to start by converting these centimeters to meters, and then we are going to use it like that, otherwise we divide by 2. So instead of using pi radius square height on 3, we are now going to use pi diameter cube on 3 times 2 is what? 6. That is why we have this, and then we are going to have that volume is equal to 1.4 times 10 to the negative 2 meters cube. Now we'll just substitute in the formula, and then we are going to have that the buoyant force FB is equal to 0.18 Newton. So feel free to conclude that option D has the correct answer. In the circuit shown in figure 4, a potential difference of 3 volts is applied across XY. What is the current in the 5 ohm resistor? Calculating the current in the 5 ohm resistor. We know from V equal to IR that, alright, okay, from V equal to IR, we're just going to have I equal to V over R. And then let's now calculate the current through the 5 ohm resistor. It's just going to be equal to what? The voltage 3 volt divided by the 5 ohm. So we're just going to have 3 over 5 ampere. Option C is correct. Simple. You can take a short break, drink a glass of water, continue. When alpha particles are directed onto atoms in a thin metal foil, some make very close collisions with the nuclei of the atoms and are scattered at large angles. If an alpha particle with an initial kinetic energy of 5 mega electron volt happen to be scattered through an angle of 180 degrees, which of the following must have been its distance of closest approach to the scattering nucleus? Alright, so let's go. We assume that the metal foil is made up of silver, and then we'll find the distance of closest approach. Now, to find the distance of closest approach, we need to start admitting that this particle obeys Coulomb's law. Let's give the statement of Coulomb's law. We know that the magnitude of the electrostatic force between two charges is given by what they prove. The magnitude is directly proportional to the product of the magnitude of the charges, and then but inversely proportional to the square of their separation. Okay, but now Q1 is an alpha particle, and then alpha particle is a helium nuclei, so it's 2e. Meanwhile, cure 2 is we're told that is what, silver, and we're given the Z of silver to be equal to 50. So that's what we are using. And now we know that E is the same as the charge of an electron now is equal to 1.6 times 10 to the negative 19 coulombs. Now we'll just substitute in the equation. And after substituting in order to find R, where R is the distance of closest approach, now we have that R is equal to the square root of K Q1 Q2 over V, numerical application. So we have our correct answer, option B. Which of these substances is a crystalline solid? Now, this takes us to start thinking about the type of solid. And then let's remind ourselves that there are only two types of solid that can exist. We can either have crystalline solids or amorphous solids. A crystalline solid is a solid material whose constituents are arranged in a highly ordered microscopic structure, forming a crystal lattice. So only crystalline solids can form crystal lattice. So let's start evaluating from A to D, which of them can form crystal lattice and which of them cannot. Wax is an amorphous solid, so it is not crystalline. Wax is an amorphous solid. Waxes lack an organized crystalline structure, and this makes waxes to be what? Amorphous solid. B, glass. Glass is not a crystalline solid. It is rather a transparent amorphous solid. Amorphous solids have a range of temperature melting points. Rubber also lacks a crystal structure, and then this makes rubber to be an amorphous solid. And then iron is a crystalline solid. This is because constituent particles of iron are arranged in an ordered structure and it has a crystal lattice. So our answer is D. Question number 20. Two resistors, P and Q. The resistors P, Q, R, and R in the circuit of figure 5 have equal resistances. The battery of negligible internal resistance supplies a total power of 12 watts. What is the power dissipated in resistor R? Let the resistor P, Q, and R have the resistance small r. Since they have the same resistances, they have equal resistances. Now the effective resistance across the source is given by R effective resistance is equal to, is given by this relation. And then let's find the current down the source, S. So I'm going to have the current down the source S, Is, to be equal to the square root of 8 divided by R. Since Q and R have equal resistance R, each of them draws a current of I, which must be equal since they have the same resistances and they are supplied by the same source. And then now they are going to therefore draw the same current, which is given by half Is. Now the heat dissipation in R can now be determined and is given by this relation I squared r is equal to 2 on r times r. Remember that I is equal to 2 over r, and then when we square it, the square root is going to vanish. We'll just be left with 2 over r without square root, then times r, because we're multiplying the resistance and the current, and this gives us 2. This gives us 2. Then we'll attach the unit of watts, and our answer is 2 watts. And then the option with the correct answer is A. We're left with 10 questions to complete this paper. The root mean square velocity of oxygen having a density of 2.1 kilogram per meters cube is 535 meters per second. What is the pressure of oxygen molecule in Pascal? The expression for the root mean square velocity of a gas is given by this. Now, where m is the molar mass, r is the ideal gas constant, which was given on the first page of our question paper, and then this URMS is the root mean square speed. So from here now, we are going to have this relation for P, where P is the pressure. Now, and then we are going to do numerical application to find the pressure in Pascal, and pressure is equal to 2 times 10 to the power of 5 Pascal from our numerical application. Two times 10 to the power of 5 is option A. On a planet with an unknown value of acceleration due to gravity g prime, the period of a 0.65 meters long pendulum is 2.8 seconds. The value of g prime is, this is going to be so simple. We already know that t is equal to 2 pi root L on g, and now we're talking of g prime, not g. This means that t squared is equal to 4 pi squared L on g prime. After squaring, and then we have this expression for g prime, and then numerical application, we have that g prime is equal to 3.3 meters per second squared. And then question 23, a cylindrical piece of soft electrical conducting material has a resistance R. It is reshaped by heating so that its length doubled, but its volume stays constant. What is the new resistance? Let's make use of the equation. R is equal to rho L on A, where R is the resistance, L is the length of the wire, and A is the cross-sectional area of the wire. Then rho is the resistivity of the wire. Now, we are told that this piece of conducting material has resistance R. It is reshaped by heating such that the length doubles. L becomes 2L. So let's see what happens to the resistance if L becomes 2L. Therefore, since the length of the wire is directly proportional to the resistance, an increase in length will lead to an increase in resistance if the cross-sectional area remain constant. So once the cross-sectional area remains constant, if the length of the wire is doubled, the resistance equally doubles. So we have 2R, option B. A heater for a shower has a power of 8.0 kilowatts. It raises the temperature of water from 18 degrees Celsius to 34 degrees Celsius. What mass of water passes through the shower per minute? Alright, this is an interesting question. We are required to calculate the energy flow rate. Now, from this equation, K equal to mc delta theta, and then we all know that P is equal to Q on T. So we can start substituting. With the mindset, with the idea that what we need is the mass of water that passes through the shower per minute, after every minute. So we are going to convert this per minute to an hour, knowing well that 1 hour is the same as 60 minutes. Therefore 60 minutes is this. Therefore 1 minute is the same as 1 divided by 60 in hour, and then we have this as m, and m represents the mass, which is the same as 119 grams. 119 grams. I'll leave my answer in grams because I can see my answer here, option A, correct. Otherwise my answer is 119 or 0.119 times 10 to the negative 3. 119 times 10 to the negative 3, which is the same as 119 grams. So we'll leave option A as the correct answer. They have a negative temperature coefficient. Okay. Now, what is the meaning of negative temperature coefficient of resistance? It means that the resistance decreases with an increase in temperature. Means that when the resistance decreases, the temperature now increases. And for this set of alternative, A and B have insulators and semiconductors have a negative temperature coefficient of resistance. But now let's have a slight negative temperature coefficient of resistance, while metals have a positive temperature coefficient of resistance, meaning that for a metal, when the temperature decreases, the resistance decreases. But now insulators and semiconductors have a negative temperature coefficient of resistance. Which of the following is an acceptable condition for the equation A minus B equal to this to be considered homogeneous? So we have another question on homogeneity. We'll start by cancelling this y. For this equation to be homogeneous, what is the condition? The base unit of the additive terms of the physical quantities on both sides of the equation must be the same. It means the base unit of A must be equal to the base unit of B, which is equal to the base unit of all these terms. Now A says A and B do not need to have the same unit. Who told you? A and B will instead must instead have the same unit. Reason why we have already annulled, we have already eliminated option A, and we're left with 3 options to choose from. Now, option D is also going to be eliminated because it says the unit of A and E raised to the power of T on CD must be the same. It must not be the same, even though it could be, but it's not a sufficient condition for us to say that it is homogeneous. So now let's look at the other 2 options that are left. Okay, we'll look at option C, which says the base unit of T and CD must be equal, which is not also a necessary condition. The base unit of T and CD must be equal, so we can eliminate it because it must not be equal. It's not a necessary condition to show that this equation is homogeneous, and therefore our correct answer will be C. The base unit of A over E to the power of T over CD, all of these, and B must be the same, which must also have the same unit with A. Therefore, option C has the correct answer. No, this is the question. Question 28. One mole of an ideal gas is at a pressure of 5.4 atmosphere and a temperature of 22 degrees Celsius. If the gas is heated at a constant volume until the pressure triples, what will be the final temperature? Given data, we have collected our data already, and then we are told that the gas is heated at constant volume until the pressure triples. It means the pressure triples. P2 is now equal to 3 P1. P2 becomes 3 times P1. Now the formula to calculate the final temperature is given by P1 over T1 equal to P2 over T2, where T2 is the final temperature. So this is that our formula. P1 over T1 is equal to what? P2 over T2. Now, but we know that P2 is equal to 3 P1, so we can substitute it there, and then we are going to have T2 to be equal to 885 degrees Celsius, and then we have our correct answer, option D. Let's look at question 29 together. The work function for rubidium is 208.4 kJ per mole. What is the minimum amount of energy needed to eject a single electron? Okay. The given parameters are energy to remove 1 mole of electron. The energy required to remove a single electron, therefore, will be equal to En. And this En will be equal to the energy taken to remove 1 mole of the electron divided by the charge of that electron. Therefore, we are going to have the energy required to remove 1 mole of an electron, which is given 208.4, then times 10 to the 3 kilojoule times 10 to the 3. We'll convert this from kilojoule to joule, and then we'll divide it by 6.02 times 10 to the 23 and see what we have. Now we continue from here. We know that E is equal to what? H C over lambda, where H is what the Planck's constant, and Planck's constant was given, C was also given. So calculating this will just fit in the value. C is the speed of light in the vacuum, and our E is equal to what, 3.46 times 10 to the negative 22 kilojoule. Then now we're not looking for this energy, no, rather we're looking for the minimum energy that is needed to eject a single electron. So let's fit it into the formula. Where H is the Planck constant, C is the speed of light, and lambda is the wavelength. The wavelength is calculated by lambda equal to hc over E, and then we are going to have this wavelength to be what, 574.5 nanometer. And from here now we can calculate the minimum amount of energy needed to eject a single electron, which is going to be 3.46 times 10 to the negative 22. Otherwise, from this formula we start calculating the wavelength, which gives us 574.5 nanometers, and that's the wavelength that we use here in the place of lambda, and then to have our energy of 3.46 times 10 to the negative 22 kilojoule. Therefore, we have the correct option in B. 3.46 times 10 to the negative 22 kilojoule. Here we have the last question. I read: two capacitors of capacitances 1.0 microfarad and 2.0 microfarad are each charged by being connected across a 5.0 volt battery. They are disconnected from the battery and then connected to each other with resistive wires so that plates of opposite charge are connected together. What will be the magnitude of the final voltage? The 2.0 microfarad across the 2.0 microfarad resistor. So we are required to calculate the magnitude of final voltage across the 2.0 microfarad capacitor. I'll leave you to solve this and drop your solution in the comment section. I would like to see everybody's solution in the comment section, while I will come up tomorrow morning. I'll come on tomorrow morning to solve just question 30 after to correct after you must have already dropped your solution in the comment section to correct. So do well to subscribe to the channel so that when I upload that, you shall be notified to come and watch. And then equally, the next video that I am going to be uploading to this channel is going to be the solution to FET, Faculty of Engineering and Technology, FET of Boya 2019 session. And then so subscribe to the channel because I'm going to be uploading videos to the channel non-stop. Thank you.